empezáis la sesión cuando queráis, ¿de acuerdo?
Ok. ¿Estamos en directo entonces?
En teoría sí.
En teoría. Los experimentales no estáis en directo. Pues vamos a esperar un par de minutillos más, por si acaso se animan algunas personas que dijeron que sí, que les apetecía, pero que tenían una agenda un poco complicada. Y aprovecho para preguntaros si tenéis alguien, quizás José Manuel, si estás escuchando el vídeo, yo lo estoy escuchando retrasado.
He silenciado.
Soy yo. Era yo, disculpad. Entonces solo me escuchaba yo, claro. Vale. Lo he cerrado, espero que no haya ningún problema. Yo lo que había pensado para esta sesión, que es así un poco informal y en la cual los dos ponentes van a estar intercambiando sus papeles alternativamente, que hagamos preguntas más o menos libremente, pero quizás dejemos las preguntas más filosóficas, más abiertas, más grandes para la discusión y quizás hacer las preguntas más técnicas durante la charla, ¿no? Si es una cosa, una calificación sobre una cuenta o sobre un modelo en concreto, lo que sea, y las preguntas más globales quizás para la discusión. Pero vamos, esto es mi...
Eso es exactamente lo que habíamos hablado Pere y yo por email, que intervenciones relativamente cortas no nos importa durante la presentación, pero si algo se va a alargar bastante lo dejamos para el final, si terminamos de contar lo que tengamos que contar y luego podemos discutir lo que sea.
Estupendo, pues entonces lo fijamos así. Si la organización y los ponentes están de acuerdo y nadie más se queja. Estupendo. Pues ya se van acercando los 5 minutos pasados de la hora, así que si os parece bien, podemos comenzar. And then I switch to English, and then I welcome everybody to this new CAPA seminar on its informal type of streaming. Today we have the immense pleasure of having 2 speakers and not just one, and very close to our hearts and institutions. So first we have Pere Masjuan, who actually was the person that triggered this seminar. So thank you very much, Pere.
Welcome.
Pere did his PhD in, for those of you who do not know him, although I think most of you might, but since we might be having some speakers, some listeners there in YouTube, let me just devote 1 minute to introduce to each of them. So first of all, of course, Pere Masjuan, who studied physics in Barcelona and did his PhD in the Instituto de Física de Altas Energías, IFAE, in Barcelona as well. Actually in my office, if my memory doesn't fail, so a little bit after me, under the supervision of Santiago Peris. And he was actually a very brave student who decided to go into the most complicated part of quantum field theory nowadays, which is non-perturbative quantum field theory, and on something that actually exists, which is quantum chromodynamics, right? So he studied phenomenology of QCD in the non-perturbative regime, and lately, or not so lately, has been trying to use his knowledge to unveil new physics, so physics beyond the standard model, using all the tools that he has been gathering throughout these years. So I think he's back to Barcelona, but only after a world tour that allowed him to stay a few years in Granada, in Vienna, and in Mainz, right? But now he's back in Barcelona. We hope that for good. And so yeah, again, thank you very much, Ben. And let me just briefly introduce the second speaker. I think it also doesn't need much introduction because he's from home. We are talking about Alejandro Vaquero. And Alejandro studied here in the University of Zaragoza and did his PhD here with Vicente Azcoiti, which I think he's still not here, perhaps, but he will, I hope he connects later. And he has been also working on QCD, on the most complicated piece of quantum field theory that actually is worth, we know is worth studying because it exists in nature, QCD. But he was always trying to master and mastering, to some degree, the tools of a lattice QCD, so using computers to compute from first principles the implications or the phenomenology of QCD. And he has become a world expert, and he is the man who talks to computers in many of these collaborations. And this a little bit off topic, he enrolled on a very different quest, and he started to work on axion cosmology with me and some of my colleagues. So he has also a different interests. But very recently, he has been involved in this thrill, like Pere, that has gathered us together here, which is this continuing disagreement between the predictions and experimental verifications of the size of the anomalous magnetic moment of the muon. And so we thank you very much, both Pere and Alex, for being here. And please, this is your stage, and do as you wish to introduce the topic to us, and then we will have a brief discussion.
Thank you, Javi. You are very kind. Nice words, nice introduction. Ari, it's actually my pleasure to be here. Thanks for that. Thanks for the opportunity to discuss this topic with you. I hope you can see the slide. Yeah, perfect. And I also like to thank you, Javier, for this initiative you got to do this sort of this discussion session with Alex. That was also a pleasure to have the chance to discuss with him by email and get a bit deeper into topic that for me is not that common, that is in the lattice QCD, as we will see. No, well, let's go to the business. That's the idea is to present the news from the muon g-2, and those news comes from different aspects, as you will see. There's experiment theory. There's different points that are important. No, but why to talk about g-2 right now? No, well, at least if you are looking at the media, you will see that indeed. Even the regular media has gathered a lot of say news on that. No, I just got few of them: El Periódico, El País, Ara in Catalunya, y El Mundo, where they got attention to that. No, so maybe because they are already titled about COVID, but they also look at that, and that was surprising. I like the title they put. No, one of those, for example, this one in the El Mundo, is using the rebuild word to refer to the muon, and using the R from Einstein. I find it very, very nice. So, I mean, the media got attention to that. Why is that? Well, because the thing we are going to talk today is a sort of simple thing, which has been very, very important for particle physics since almost the beginning of the quantum field theory. No? Or actually from the beginning, no? And that's what we are going to talk today. No, not about spinning tops, that was a joke, but that's the idea. No? So we are going to discuss this Fermilab's muon g-2 release, and then we will go to a scrutiny of the standard model with strong and weak points, and just a sentence on new physics. That's a disclaimer. I'm not an expert on new physics. I just wanted to put a reference thing. For open the discussion. So we are going to center in the standard model, and that's the idea. No, the g-2 is very important because, in words of Arkhadiev Einstein, with the precision we have right now, the experimental precision, the g-2 is the particle physics in a nutshell. So everything that we know about quantum field theory goes there. That's why it's so appealing, so interesting, and that's what the actual object we are talking about. No? So as soon as you have a particle that has electrical charge, mass, and spin, and you will have a factor G called the gyromagnetic ratio relating the magnetic moment with the spin. And as soon as you put this particle into a magnetic field, you will see that this object is going to start precessing because of that interaction. If the theory would be the Dirac relativistic theory in the early in this 20th century, you would predict actually that this factor G is going to be equal to 2. But as soon as you introduce quantum field theory, say radiative corrections, if you like, you're starting to see that these objects are have inner structure, for example, the spin, but also these surrounding photons and all these things, you will see that the G is not equal to. And that's what you are looking for in the experiment and in the theory. And this is an example, the first loop correction to that would go to this factor G. And the quantity, this loop, this is your muon or electron. In blue, you would have your magnetic field, and that's the photon. So you will have this loop, and that's a small correction, but it's calculable, and already Swinger did it many years ago, and that's the amount, no? 10 to the minus 3. So we are going to look for precision at least 10 to the minus 3. Okay, that was very challenging at the moment where Dirac predicted G equal to 2, but as we'll see soon, there were a departure, and actually the departure is accounted for by this coefficient A, which is G minus 2 divided by 2. A is called the anomalous magnetic moment, not because of a quantum field theory anomaly. It is anomalous because it's a departure from the Dirac theory. That's the idea. Okay, and I just want to put a historical word, no? When before the Dirac theory was there, G was understood to be 1. No? It was the Dirac who proposed the relativistic theory, confirmed then by experiment to see that, to observe in nature that actually spin 1/2 relativistic theory was the theory. But then later on, they got experiments precise enough to start seeing the departure, this thing, no? Plus the theory, plus the lamp shift, plus the theory corresponding was the trigger for the quantum field theories. Curie in particular at that moment, and then the Gibbs theory, Standard Model, and so on. So the same experiment that at that time gave the credit to the relativistic theory, later on was precise enough to say that was not the last story. And what we may have started to see right now is that the very same concept, the very same experiment is telling us that maybe quantum field theory in the form of the Standard Model is not the last word. I like to give you some hint what was the perspective before the Fermilab experiment that came on the 7th of April. What was the image? What was the landscape? And why is that so important, the Fermilab number, the experimental result? No? Before that, we had a previous experiment performed at Brookhaven National Lab that has actually an error 6 10 to the minus 10. Okay, which is very precise, 10 to the minus 10. A lot of figures here. No? And we also had before summer 2020, we had a scattered Standard Model predictions. No? There was not really a consensus. There were different reviews that they were getting a sort of similar error size, 10 to the minus 10, also 6, but the central value was different. No? And then you put it together to say that there was a discrepancy theory in experiment of between 3 and 4 sigma. As you can see, this is not it's not a fixed number. No? There was, depending on the review you would take, there were fluctuating discrepancies here. No? So, but still, you wanted to clarify. So there was this intention from both theory and experimental communities to improve those results, and they decided that in order to observe whether this discrepancy would dilute or would increase to 5 sigma, you would need a precision 1/4 of what they had, both theory and experiment. No? So they fixed these goals, and then last summer, the theory community gathered, part of the theory community involved in this business gathered together to release this theory initiative white paper, where there you would find a sort of consensus for this Standard Model contribution. The Standard Model, we'll see later, is not an easy thing. So it requires a lot of decisions. and they got it, and they got a value with an error 4 instead of 1.6 that was the goal, but okay, going to the right direction. No? So the idea of the Fermilab National Lab result would be to go for a parallel or counterpart of the theory.
Excuse me, Pere.
Sí.
What is 10 to the minus 10 is delta A, no? Not A. X,
Correct. 10 to the minus 10 is only the precision. You are right.
No, but this is delta A, the difference, no? between the experimental value and those predicted, and the one predicted by the standard model.
That's correct. The uncertainty would be 10 to the minus 10. Then this number starts already at 10 to the minus 3.
Ah, okay. Thanks.
Yeah, you are correct.
Yeah, okay,
Super. Yeah, sorry for if I confused you. Yeah, so the precision is 10 to the minus 10, but you have a lot of figures.
Yeah.
So it's really a huge effort. Okay, thank you. And that was the Fermilab release, no? And you can see that was the plot from their publication. They also show it in the press release and in this forecast they gave, where in red you have the Fermilab result. Blue would be the previous Brookhaven one. You do average, and then you get the purple. And then you compare with this number I was showing from the standard model. As soon as you compare, you get this 4.2 sigma that reached the regular media, no? All these journals I was showing you before. No? So this 4.2 sigma means that the difference between the theory and experiment is 25 units in 10 to the minus 10 with an error of 6. Okay, and what is nice is that as it happened in the previous experiments, for example, in the Brookhaven, the Fermilab only measured right now the muon plus, the positive muon channel. And as it happened in Brookhaven, you would expect that as soon as you would be able to measure the negative muon, you would also be able to dramatically reduce the uncertainty, on top of all the data you are going to accumulate during the lifetime of the experiment. I also like to say that there will be a forthcoming experiment in Japan, in the J-Park facility, that is completely different setup. It's a completely different method for studying the same object, would be different systematics, but they expect to have similar precision, as you can see here. And I'm not going to talk about that, but I have some backup. If someone is interested in that, we can discuss it later. But that would be very important. And as you say, they believe to start.
Actually, Pere,
sorry.
If you will allow me just to intervene for a second, it's going to be very interesting to have totally different experiments, because a flaw that you can see very clearly in the previous slide, you can go back to the, exactly there. The BNL experiment and the Fermilab experiment, they are very, very, very similar, and they use the same muon storage ring. It was quite a story how they had to move this ring through the whole country. They had to take in a boat and then through land. So these experiments, most likely they have very, very similar systematic errors, and most likely these results could be correlated somehow. So we need to be very careful when we take this experiment average to reduce the errors, because these experiments, I wouldn't consider them as independent. So it's going to be very interesting to see new experiments based in totally different technology, that they do something else, and then they have very different systematics.
Can I make a remark here?
Sure.
This question was discussed in various presentations, and I remember that one of the spokesperson of the Fermilab experiment heavily refuted the claim that the two experiments are effectively the same, that the systematics are possibly the same, that even the people are the same. Yeah, he nearly got angry when this remark was made. And it's true that the magnet is the same, but it was completely newly measured. Yeah, about the magnetic field. All the other experimental setup is new. People are effectively new, and I think the idea how to do it in principle, of course, is the same. Yeah, to keep the muons there, to measure how they decay, etc. This is the same, but it's only the idea, and therefore, I think one should consider these two experiments as independent ones. of course, it is still very important and very interesting to have a completely different experimental setup.
Oh, definitely.
Also, yeah. One can discuss pros and cons there as well. Yeah. I don't refute this, but to say that one should be careful with the interpretation of the uncertainties because the experiments are too similar, I don't agree with this.
Just to add on that discussion, I forgot to tell that in both here you have the numbers of both collaborations or both experiments, Brookhaven and Fermilab, and there are two different sources of errors. The first one is the statistics. The second one is the systematics. And as you can see, as soon as you combine the errors in both cases, the statistics dominate. So if that might be a part of this systematic error that may be correlated in a way or another, you will not see it, I would say, in my opinion, because of the being dominated by statistics right now. But I will like this to discuss a bit more about the experimental setup soon. Let me
excuse me, I have a question.
Sure.
Do you know if this future Japanese experiment is different from Brookhaven and Fermilab from the technological point of view, or are there differences also in the methods used to measure?
Everything is different.
The anomalous magnetic moment.
Everything is different. That would be a penning trap. Can we postpone the discussion for later on? Because we have these slides and the backup, but I can already anticipate. It's not going to be a ring, toroid, but it's going to be a penning trap with Linux. So it's completely different. They are slowly muons, shortly lived. So you will see. If you don't mind to wait until the end, we can discuss in the discussion session.
This is leading to a very nice discussion, so let us just reserve it for later.
Yeah, because I have the backup and we can do it. I have the picture of the experiment. It would be nice to discuss with you guys. Yeah, as I was saying. Okay. What are they measuring? How do they do that? Huh? That's the idea. In both Brookhaven and Fermilab, as Alex was saying, they would use the same framework. That's a ring. With a strong magnetic field, 1.5 Tesla, and then you will have your muons coming from a pion beam. Muons would be kicked in to this ring, and they would say start oscillating here. No, they are very boosted. You can see that their lifetime would be enlarged by a factor 30. That's a relativistic gamma factor of around 30. They are very boosted, very energetic ones. So you have a lot of time for them to observe them how they behave. And then we are going to compare two different frequencies here in this problem. One is the frequency of the full rotation, cyclotron precision, that's well known. And then you will have the other one, the spin precision. And the fact that having a magnetic field, a strong one, you will say that by conservation of momentum, the spin is going to start, the spin axis is going to start rotating around the momentum line. If there will be no any sort of internal structure of this particle, for example, G would be exactly 2, you will see that both frequencies are the same. And when you measure omega A, you will see 0. And we are now going to see this omega being different to 0. And that's a signal of A. That's you can realize now why what is important. Why do we define A? Because there's actually G minus 2/2 that appears in the formula, right? So that's a very important thing here to keep in mind, and that because something may trigger discussion is that, well, okay, you're coming with your pions would transform into these muons, and then you put your muons into the system, but then you want to really focus those muons to be say collimated in your setup. For that, you need a focusing system, and you are going to use electric quadrupole fields. And then as soon as you put them, you will see that they may contribute to this frequency you like to measure. So you don't want that. And since you don't want to have any electric field, a nuisance there, you are going to look at what relativistic gamma factor you need to actually cancel all this term. Here, gamma is the relativistic gamma factor. So you just look, what is the energy I need those muons to be traveling in such a way that this term is 0. Okay? And actually, that's called the magic momentum which is exactly the one I was showing you before, this factor almost 30. So that's why you select the pions to be at that energy. Okay. Of course, you can say, hey, how can you know in advance what value do you need to have? Okay, yeah, okay, that was not the first experiment. There was a lot of tryings before, so they already got an idea how much is that. On top, that would be a systematic error if you see departuring of or the opening of your beam inside the experiment. So you really need to calibrate very well this thing, but you can do it, and that will be a systematic error. Okay, as Alex was saying, the magnet is actually the same as was used in Brookhaven. They move it by boat, as Alex was saying nicely, and here in this web there are many nice pictures of that. And then they go there, they start they calibrate it and start measuring. What happens there is that in your ring, your muons are going to decay into electrons. Electrons are lighter, so you are going to catch them in your calorimeter. Okay. And then you start counting things. And then there you have many muons. So you start seeing an oscillating pattern with respect of the line between momentum and spin. No? And then you will have these lines here, that seems a solid line, but it's not a solid line, it's really experimental dots, experimental points, but they are so condensed, so precise that it seems a solid line. So you are going to fit this thing with the standard exponential decay formula, and then you will get your frequency there. Okay, so that's actually not what they do, because to use this formula properly, you would really like to have a very under control your magnetic field, and you will not have a magnetic field with a precision 10 to the minus 10. That's what you need for the experiment. So you are using another technique that is actually calculating mu via ratios of things. No, you compare the omega A in this data with respect of the free proton precision frequency that you can also measure with the same magnetic field, and that's actually then the number that they measure. Okay, that's in the Fermi lab, and that was in the Brookhaven. You can compare, and from that they would get mu. With a lot of systematic errors, no? As you can see here, a lot of sources, of systematic errors that they have taken into account to get the final error. No? Very good news. What they released the other day is basically 5% of the data they believe they would get for the whole life of the experiment. Just 5%. That goes under the name of run 1. Even though they already have run 2 and run 3, I think, on tape, not yet analyzed. But they say that if, as soon as they really run 2, they will have double statistics. So in a couple of years, basically, they are saying that if nothing else changes, you may start seeing not 4.2 sigma, but something larger, no? Which is putting a lot of pressure to the theory guys, to the theory community, to really do the same effort reducing the errors. No? They are working very fast at Fermi Lab. So that's the actual magnet with very nice picture. You see this size of the experiment, and those are the 3 points that Fermilab improved with respect to Brookhaven. First, you have much more muons. Then you have a better uniform magnetic field, and finally, you have a better precision frequency measurements. From the theory side, already announced the last summer, we got with the theory part of the theory community released this white paper. You can see here Alex and myself as authors. Was a very nice, interesting work here to get consensus, a sort of consensus, which is very difficult. And that's how the thing looks like. No, as I said before, the standard model appears all together in this g-2. So you have to calculate all the possible contributions, sum them up. And then you get a number, This is my contribution in this Hydronic by Light, which I'm very proud. We got into this white paper, and that's the number. Okay, not yet the goal we got, but it's pretty going on the direction we want it. To calculate the hadronic, the anomalous magnetic moment, you will have to take into account everything. By the structure, by the phenomenon we are discussing, as you can already anticipate, the QED is going to be the largest contributor here, 99%. I don't know how much, but it's a lot, no? And actually, it's very well known. You can see this is the contribution, this is the error. But since we are going for a precision of, in units 10 to the minus 11, a precision around 40 10 to the minus 11, Electroweak sector, for example, is super important. You see the amount it contributes, no? Which is now very well under control. And as you can see by the errors, the largest uncertainty from the standard model comes from an object which is not really contributing very much, but has the largest error, that is called hadronic vacuum polarization. That is simply the fact that as soon as you have a photon in the loop, this photon can see, say, leptons, electrons, muons, and tau, of course, but they would go into QED, but they can also see quarks. And as soon as you have quarks, then you will have to discuss how do you hadronize those and so on and so forth. But you sum up the different contributions, including subleading higher orders effects in the hadronic sector, and then you will get the number. No? The QED is well under control. It's completed 5-loop result. That's amazing work. So many diagrams, and which is basically cross-checked fully at the 4-loop and part of the 5-loop as well. QED has a part that is actually universal for all leptons. Could be a muon, could be an electron or tau. You would have this common piece for all of them, but there are other pieces that are depending on the ratios or the different masses appearing in the loops. So that prevents a naive scaling of a g-2 for the electron and the muon or the tau, for example, via the ratio of masses. No? Those are examples of the second order. Okay, and as you can see, there are many things with photons, but then at some point you will have vacuum polarization insertions that would be different depending on the species you are discussing. And this is an example of the topologies for the 5-loop. So there are more than 12,000 diagrams to calculate. So that was enormous work. For the electroweak sector, as I commented, the thing is well known and under control up to second order loop correction, and you can see here the examples of one loop. And I just like to say that because of the being a muon and then you have a vector here, you will have to, in order to have the loop, you will have to pay a price that goes with the proportional to the lepton's mass square. So the contributions will be very small. You see that's the G Fermi and that's the lepton mass. So if you would have an electron, you can see already how much would that contribute to the electron G-2. No? That is also important for the new physics contributions that may, being a vector-like, they will have to pay a price to be present there. And let me go to this hadronic vacuum polarization. That is a more controversial because it has the largest error. I'd like to scrutinize it a bit, and then Alex will continue. And the idea here is that to comment with you in a critical view, how do we get these numbers and what we can think about that. No? If you look at the recent determination of this object, it seems to be a fairly good agreement. But as we'll say, as soon as you dig a bit, there are many things appear there. No? How do you do that? So you have to, that's the idea. You would like to calculate this loop. But as I said, this loop is complicated to calculate because you are within a loop having a quarks that can run, they would have from 0 to infinite energy. So then you would like to have a theory that would be able to calculate a quark, very low energetic quarks and very high energetic quarks at once. That theory doesn't exist yet, so we don't know how to calculate it like this yet. So we are going to use an optical theorem to relate the vacuum polarization here, the hadronic vacuum polarization, via two hadronic inclusive cross-section, so measurements. No? Actually, the formula is well known, and it's an old formula already, where you can see here the result of this loop dilated to the A mu as an integral of a kernel that is kinematic kernel and a hadronic cross-section. That's the inclusive hadronic cross-section. Both are 1 over S, so it's the integrand is very well approach, or is picked at very low energies. That will be the most important region to explore in this setup, in this framework. Okay, this is a couple of plots from the white paper where you can see the effort that the Masjuan machines did to get precise data for that region you would like to integrate on. And this is how the thing it looks like for one of the examples from the white paper, for one of the collaborations performing these things. What is the situation here? you are going to have you need E plus E minus to the inclusive hadron, so all hadrons at once. But you don't do that measurement. What you are doing in the experimental setup is looking for channel by channel and then summing up, and that's what you have here. You start E plus E minus, and then you start collecting data for the different channels, and then you would put these individual channels into these integrals, and then you will calculate their contributions, and then at the end of the day, you will sum up. Since we don't have data from 0 to infinity, but from 0 to particular energy, sorry, from that point on, you are going to use perturbative QCD, and then you will sum up. Okay. You can see here in this chart that this is the energy contribute to the integral. You should integrate from the threshold to pion threshold up to infinity, but reaching say 1 GeV is 75% of the integral. That's where you really like to have the most precise data. Okay, so I'm showing you only the result of one collaboration, Keshavarzi et al., where they got this number that comes from these edges, as I showed you, this called the so-called hadronic vacuum polarization at leading order. But you would like to have you may have more contributions subleading in the electromagnetic counting, so having an extra photon or having two insertions, one hadronic vacuum polarization, but with a lepton vacuum polarization, and so on and so forth. So the extra contributions that would only modify your kernel of the integral using the same experimental data. So you do that, the kernels are known, so you sum up next to leading order, next to leading order, you sum them up, and then you would get this value. Okay, this number should be basically this red one, but then you go to the white paper, and then you see that actually the error is not 2.5. So by combining these two edges, but it's somewhat larger. Why would that be? If I'm averaging these two numbers, the error should be much smaller, not much larger. No? Okay. What happens here is that as soon as you look at the detail, it happens that the central values of this determination are pretty much the same in these two different collaborations. But as soon as you look channel by channel, you see discrepancies. And let me point out to the largest of those. The largest contribution to the hadronic vacuum polarization goes with 2 pions, pi plus, pi minus. And as you can see here, the amount, it's that the global thing is almost 700, 500 goes by these pions. And there are these two results using the same experimental data, and the central values do not coincide. And the difference is larger than any of the errors they quote. So in order to then reach a sort of consensus, how do you average these things? You cannot just purely average these numbers. You have to arrive to some agreement. What the white paper decided was to combine these numbers and half of the difference attributed to the systematic error for each one. So basically what happens is that you can, to get the 40 or 4 10 to the minus 10, you would basically combine these numbers in quadrature to get the error. No? Not much the uncertainty of each channel for each of the collaborations, but it's different. It's different because when the numbers would agree, the error would be reduced. When the numbers disagree, the difference dominates. That was the strategy, which can be discussed. And actually, I personally would have done it slightly different. And since I see these differences as a systematic error, which basically mean a systematic error on the data, as I will show you, I would have taken them combined linearly instead of in quadrature. And that's why I'm giving you, this is my number. That's the white paper one. This is my number. I would have done a combination in linearly, so to be more conservative. And that's actually the summary. Why those numbers are different. You can see, to get these numbers, you are going to average different meson machine results for the same channel. And you see the tensions here between Babar and Chloe. This difference is 10 in 10 to the minus 10. It's a large difference for a very small region of energy. And as you can see in this plot here, no, where you compare data in green with the data in yellow. They are supposed to be the same object, but the differences are large and actually very large, no? As that large that if you say neglect Chloe, you would get the average here in this rectangle. And if you neglect Babar, you would have this average here in red. No? So the numbers are very different. And then if you want to be super conservative, that would be my attitude, you would like to take the difference, period, difference, as an extra sort of systematic error, which only means that since you cannot exclude one or the other experimental collaboration, you may have be seen here simply a systematic deviation, systematic error on the data itself. No? So you could take the difference as an extra source of error and then be super conservative and say combine in linearly all the channels plus the one from the 2 pions. No? So getting a very large error, but having all these things under control. There's another thing on top, which is goes under the tau data, which is another business, which is actually, if we would have used instead of e plus minus tau data, the number would be 700 instead of 685. So 15 units of a difference. No? So there we have here a puzzle in this, I would say, in this data-driven, and I believe Alex can tell us a potential solution right now. So I stop sharing here.
Can I ask a technical question about what you were saying?
Oh, please.
Yeah. You were mentioning the reason for using experimental data. You said because it's complicated to calculate it. I always thought the complication lies in the fact that we do not know the quark masses. I mean, the leptonic contribution is calculated, and it's the same type of diagrams. So I thought, I mean, especially the light quark masses are really not well known, and there are dependencies at least logarithmic or something like this, yeah. And but that this spoils it, and therefore we have to use experimental data. But maybe I'm mistaken, or
no.
I thought the diagram could be calculated as such.
No, you are very right. That's the simple quark loop diagram with all the corrections you can imagine, and that's for perturbative QCD where quark masses are large enough. That's fine. Actually, you would do that for the charm. For the bottom, you do it by you calculate. I
think the top mass is used at least the top mass is calculated like this.
Also, bottom and charm. That's sort of easy because you really have an expansion of those diagrams in terms of the alpha strong. You can do that. The problem, as you were saying, is what do you do with light quarks, where you have a problem with how would you define the alpha strong for some light object? That's the problem. So the problem is actually the 75 of the ballpark of the integral, which is the very low energy part, no? Where you could actually calculate, but you don't know how to. You would be in a regime where alpha strong is too strong, so perturbative QC doesn't work. So you can say draw the diagram.
Yeah.
But
you can calculate the diagram, but you just don't know what to insert for couplings and masses.
Correct.
Okay, thanks.
Thank you.
Yeah, I will also add to that before starting my part of the talk, that in Larynx QCD we can compute the quark masses with relatively high precision. Maybe not enough for these g-2 purposes because we're shooting very very high, but we can do very precise calculations of the quark masses. So the problem, as Pere was mentioning, was in the non-perturbative part of QCD at low energies. That is not about, I mean, you have an infinite number of diagrams contributing there, right? You have a mess of quarks and gluons because alpha strong is too large. And then you can, I mean, how do you calculate that? You need to use a non-perturbative method, which connects to my talk. So let me share my screen. And let me start before this seminar becomes too long, although it's certainly becoming really, really interesting. And I have this slide, which is something very similar to what Pere has already shown, of the different contributions to the anomalous magnetic moment of the muon. And as a short reminder of what he said, the most important contribution comes from QED, which starts at order alpha. It's very well known, and have here some references. Pere has given much more detail on the reference than me about this. And this contribution is very well known at 0.001 parts per million. And there are a small issues here with the tensions in the determination of alpha electromagnetic. I'm not going to get into that, but there were recent experiments that show that there are 5 sigma tension in the super accurate determination of alpha electromagnetic that are being done nowadays in state-of-the-art experiments. This shouldn't affect too much g-2 for the muon, but certainly if you look at g-2 for the electron, there might be consequences there. Then the next contribution we should take into account is the weak contribution, which starts at alpha electromagnetic square. And this is also very well known at 2 loop. And again, Pere gave very extensive references about this calculation. And this is the relative size of the contribution. And it's also well known. It's known at 0.01 parts per million. And the problem comes with the hadronic parts that are not so well known. So we have 2 contributions here. There is the hadronic vacuum polarization, which will encompass all diagrams of this style. So the muon emits a photon and this hadronizes, and then it becomes a photon again and interacts with the original muon. Or the hadronic light by light, which is something a bit more complicated. And actually, it's much more complicated to calculate both in lattice or in phenomenology, which is where Pere is working on. So this hadronic vacuum polarization starts at alpha squared, the leading order term. Of course, there are next to leading order terms at alpha cube and next to leading order terms that we should take into account. And the hadronic light by light starts at alpha cube, is subleading contribution, but nonetheless, it's important to take it into account for the precision goals we want to reach. And these numbers I'm showing here are taken from the white paper that Pere was mentioning before. So let me focus on the hadronic contributions. And these are really complicated to calculate, mainly because QCD is non-perturbative. So as we were discussing right before I started, the high energy part is fine. You can treat it with perturbative QCD, but the low energy part, it's a nightmare, okay? So there are some brave souls that try to work this out, like Pere, the hadronic light by light, which by the way is the most complicated contribution to calculate using phenomenology and a variety of tools. And but essentially, I'm going to focus on the other calculation, which is I will have a few words about hadronic light by light on the lattice, but I'm going to focus on the hadronic vacuum polarization contribution, because this is what is most mature in lattice calculation. And for this, there are essentially 2 approaches. One is the dispersive approach. Pere was explaining. That involves the accurate measurement of electron-positron cross sections, and then use an optical theorem to relate this to the hadronic vacuum polarization tensor. And the other one is to use lattice QCD and calculate directly those contributions. And I have here a hopefully short introduction to lattice QCD. I mean, what do I mean by this? So essentially, lattice QCD is the best, or maybe the only non-perturbative technique we have to deal with QCD. We take the QCD Lagrangian, no approximations here, and we put it in a computer to perform non-perturbative calculations. In order to do that, because this is a theory with an infinite number of degrees of freedom, the first thing we need to do is to make this number of degrees of freedom finite. And we achieve that first by discretizing space-time and introducing a finite lattice spacing, which is an ultraviolet rollator. So we have a limit in our maximum momentum. This is something that you could do when you want to regularize your integrals. Okay, I mean, it's not something very advisable because you are losing Lorentz symmetry. You will need to recover it in the lattice spacing going to 0 limit. Okay, but some people work with this kind of perturbation theory in a lattice. Okay, so here so far we are just regularizing. We are not introducing any approximation. And then to make this number of degrees finite, what you do is you put everything in a finite box with a finite spatial volume and finite time extent. Okay, and then you perform simulations in this unphysical setup, and then you approach the physical limit. And the setup is unphysical not only because you are breaking Lorentz symmetry and you have this lattice spacing and this finite volume, okay, everything, and you are trying to recover everything in certain limits, in the thermodynamic limit and the continuum limit, but also because you can the parameters that go in your Lagrangian. You can use different quark masses, or you can change the number of C quarks that are taken into account. So state-of-the-art simulations work at physical biomasses, but this is very expensive. And normally you generate several ensembles of configurations with a variety of masses. And you use all these data and effective field theories to reach right chiral extrapolation. And with respect to the number of C quarks, state-of-the-art simulations work with 2 + 1 + 1 quark, which, let me translate this. This means there is degenerate up and down quarks in the C with the same mass. And then there is a strange quark and a charm quark. The bottom quark is not included in the C yet, but its effects should be really, really, really small. And there are other state-of-the-art simulations that separate between the up and the down quark and take into account the difference of masses between the up and the down. Of course, this difference is always taken into account, as I will explain later. Okay, but I mean, you can simulate it directly or try to correct for it after you have done your simulations. Now, the best thing of lattice QCD is that you have a great control of systematic errors. And this is done when you gather all your data by using effective field theory descriptions of QCD. These effective field theory descriptions are really good at mainly two things. The first one is they can give you an ansatz for your fits when you have done, for instance, simulations at different lattice spacings or different biomasses in order to take your data from your unphysical setup to the physical real world. So you want to take your lattice spacing to 0. You would like to know how your observables behave with respect to the lattice spacing. And this dependence is given by your effective field theory. But also you can estimate the size of your systematic errors just by going one order higher in your effective field theory and looking at the size of that term. Okay, then this gives you a sense of the truncation error. That's why these calculations are always systematically improvable. And the better computers we have, the better data we have, the better we develop our methods and our field theories, in the end, we can reach smaller errors. So now let me say a few words about the Hydronic light by light calculation on the lattice. This is something very recent. Actually, the first paper was published in 2019 by the RBC UK QCD collaboration. In this setup, we focus in these two diagrams. And the first one, which will be sort of connected, and the second one, which will be sort of disconnected diagram. There are other diagrams that contribute here that are SU3 suppressed. SU3 means flavor. This means this suppression comes because the sum of the charges of the up, the down, and the strange quark is 0, okay? And the difference of the masses is not very important for the loops we're computing here. So there are huge cancellations, and in the end, all these extra diagrams contribute very little to the final result, okay? So this is a very complicated and expensive calculation on the lattice, which involves the integral of a 4-point function, which is a devious object, very noisy, and you can understand how complicated is this by looking at the targets we have for the future in this calculation. So for instance, for the hadronic vacuum polarization contribution, we are hoping to reach sub% precision in the following years, but the hadronic light by light will be happy to reach a 10% precision. Okay, but now you have two independent complete calculations you can compare with. One is RBC QCD and the other is coming from mine. There are cross checks possible, and the coolest thing of having different lattice calculations is that since each lattice calculation uses different regularizations and different methods, you have a great control of systematics, yes, by comparing different results. Okay. And again, these are systematically improved calculations. So this is the current status, which I'm comparing here, the white paper result and the data-driven dispersive result that was published in the white paper with the lattice calculation. As you can see, the original calculation had very large errors. The one from RBC UKQCD, the one from Mainz is improving this result a lot. This was not introduced in the was not used in the average of the white paper, and we expect to improve upon that. So now let me explain how the hadronic vacuum polarization contribution is computed on the lattice. And I want to remark that we are doing the leading order calculation. But from here, once you know that the vacuum polarization tensor, you can also extract the next to leading order and next to leading order contributions. And in the plots, I'm going to show for the final results of the anomalous magnetic moment of the muon when I'm comparing lattice results with experiment. Everything will be taken into account. Okay. So we start from the 2-point correlation function of the electromagnetic vector current, and this is a tensor because this is a vector. This current is a vector, and when I say this current, I define this for a particular number of flavors. So in the current state-of-the-art calculations include up to the charm quark. Okay, the bottom quark is as a correction, and I will write this way, okay, as you for sure know, where these are the different charges of the different quarks. And if we calculate the Fourier transform of this object, we will obtain the vacuum polarization tensor. This is a tensor, but we can extract the tensor structure out of it by using general arguments of Euclidean invariance and current conservation. So in the end, what we have is a scalar function, the scalar vacuum polarization. This function is what we need to integrate with a specific kernel in order to calculate the Hadron vacuum polarization. And this is essentially what we were doing in the lattice at the beginning. So we're working with the zero-mode substrate vacuum polarization tensor, which is just something as stupid as adding a -1 here in the calculation. And since now, when you compute this and this, they are highly correlated, the errors are much smaller. And then we were extracting the scalar part by calculating the sum of the diagonal, exploiting the known tensor structure of this tensor, and dividing by q squared. And you can immediately see here a problem because you know, in the lattice, since we're introducing these regulators, ultraviolet and infrared, you need very, very large physical volumes to be accurate at a small q squared. Okay, so these results at small q squared, if they are noisy for some reason, the noise is going to be greatly amplified with this ratio in this calculation. Okay, and the problem of having very large physical volumes is that you want to have a decent lattice spacing, not to have large discretization errors. You need a lot of points. Okay, so you need huge computers to simulate this. So initial lattice methods attempt to use an ansatz for the whole region to feed the lattice data, which will be very clear in an intermediate region, not large momentum, not small momentum, and try to guess how the tail and the original the low q square region will look like, and integrate that. But that was not working very well. So some people decide to try a different approach, which will be to split this integral in 3 parts. As I'm showing here, there is a low q square region, an intermediate q square region, and a large q square region. The large momentum region can be computed in perturbation theory, and this is a small contribution. This is 2% contribution. And the intermediate momentum region is computed directly by numerical integration on the lattice, because here the lattice data is really good. And then there is this low q square region, which, by the way, is the most important one, because q square peaks, sometimes this happens. Okay, now I got the pointer back. This integrand, the kernel times the vacuum polarization, scalar vacuum polarization, peaks at around the quarter of the mass of the lepton divided by 4. Okay, and this integral dominates. It's 70-80% of the total contribution. So I'm showing here the simplification of the vacuum polarization, the scalar vacuum polarization. This is the function, okay? And this is not the whole story, because in the integral you have a kernel multiplying this, and this kernel diverges at 0 momentum and goes, I don't remember if it's 1 over q squared or 1 over q to the 4 for large momentum. Essentially it vanishes, okay? So this integrand will rise here, will peak somewhere in the low q square region, and then go down again, okay? So in order to evaluate these integrals, the idea is to relate, well, we know that this scalar vacuum polarization is related to certain functions with certain properties, and this can be well described with Pere approximants, and I know Pere is an expert about this, so maybe you can ask him about after the talk about these techniques. And you will fit the data you have, maybe in a better known region from the lattice to Taylor or Pere, and then you will use this extrapolation as the fit function. You will put it in the integrand to calculate the low q square region. Okay. You can even provide higher moments of the scalar polarization to increase the precision. There were some other suggestions on how to deal with this low q square region by Bloom and collaborators. Actually, Bloom is one of the leaders of the G-2 calculation on the lattice, to use ratio data. I don't like that, because the beautiful thing of the lattice is to have pure standard model predictions of the different observables. You don't want any influence coming from experiment. Okay. So let me explain how we can compute those time moments, and you can choose a particular Q when you are relating the two-point correlator with the vacuum polarization tensor, and using the previous tensor decomposition, you can extract a correlator that depends on time. Okay, so you can relate again the scalar vacuum polarization with an integral of this correlator. In this case, it's a Fourier transform, and from here directly, instead of trying to extract the scalar vacuum polarization as a function of the momentum and trying to do an integral in the momentum, which can be complicated on the lattice, especially at the low end and the high end, because of this infrared and ultraviolet regulator we have. You are going to stay with an integral in time, which is much easier to perform, and we are going to calculate the different moments of this scalar vacuum polarization by taking derivatives or expanding this exponential. Okay. And this can be calculated very accurately on the lattice. And we can go to high order, maybe third, fourth order, okay? And this will give us a way to construct an accurate Pere approximant for low q square, okay? Because the integrals in time are easy to perform. Of course, we need to deal with the tail at large times of the correlator. I will show later why this is a problem. In any case, these methods were used until very recently. Now, more or less, all collaborations have converged to use Bernecker and Meyer, which works in a different representation, in a time representation. Again, we start from the two-point function, and we extract a time with this. We can integrate this with a suitable kernel, and we will obtain the hadron vacuum polarization. So this is way easier to do on the lattice, I mean, accurately, because the integrals in time are momentum. But of course, we need to deal with the tail to perform such an accurate calculation. Well, the first one are these tails at large values of the time. The tail of this correlator is dominated by two pion states, as Pere has shown in the, I mean, essentially, the lattice is trying to reproduce nature here, right? Because we are working in QCD. And in QCD, if you look at the standard two-point correlations, your correlators you are computing, you can prove that the signal to noise ratio of any two-point correlator you are going to compute decreases exponentially with time. Okay, there is one exception, which is the pion, but whenever you have something heavier than a pion and 2 pions is heavier than a pion, then you are going to have an exponential decrease of the signal to noise ratio, which is what we can see here in these blue points. So you see that at the beginning, the blue points are exactly the same as the red points, which will be a different kind of calculation. And they are very accurate, but as times goes by, the error starts to increase very fast, and by time 10 here in this scale, everything is totally unusable. So you have no hope of extracting an accurate result by integrating this data given by the blue points. So how do we solve this? Well, we compute the low modes associated to our Dirac matrix to have an accurate representation of this correlator. So this is we need to calculate the eigenvectors and the eigenvalues, and then we use these low modes to have an exact reconstruction of the low mode part of the correlator. And for the high mode part, we use the same statistical methods we are using to compute these blue points, but this high mode part is much easier and much faster to compute. And so we can use the low modes that we already know to accelerate the inversions. I mean, this is calculated by inverting a huge matrix. Okay, when we are computing the low modes of this matrix, then we can use those low modes to deflate. All right, and I can show here I'm showing here the contribution of the low modes, which are those black points, and the total contribution, which are the red points. And as you can see, the error is greatly reduced by using this technique. It is very expensive, but it pays off in the end. Another technique that can be used is to do an exact reconstruction of the tail by guessing, well, calculating the states that will go here in the tail. So we know the dominant state will be 2 pion states, but there are higher states that can be taken into account. And the good thing of this method is that you can do a separate calculation to work out those states. I mean, you are not restricted by the data you have for your g-2 calculation. You can calculate other correlators, and these calculations are much easier and much faster to perform. So when you have an enough number of states, you can try to reconstruct your correlator. And for instance, here I'm showing the correlator in the black points, and I'm showing what happens if you try to reconstruct it with 1, 2, 3, and 4 states. Okay. And with one state, you need to go to very far times in order to have a reliable reconstruction of the tail. But as soon as you add 2 states, you have a very good value for the tail. And with 3 states, you can even go half, or 4 states, you can even go half the correlator. I mean, from time equal to 1 fermi on, everything is very well reconstructed. So this method is very powerful and very accurate. But we can even improve on that by using the so-called bounding method. The bounding method consists on finding strict upper and lower bounds for this correlator that will affect especially the tail. So for instance, we can say an upper bound will be the tail should decrease faster than a 2 pion state. I mean, as fast as a 2 pion state, which will be the only thing that survives at infinite times. And in any intermediate time, it should fall faster because there will be other states contributing that are heavier, right? I mean, that will give you an strict upper bound on the correlator. So you know your correlator is going to be behind that. And you can find an bound using a similar argument, and of climatic, these bounds are going to give you information, a lot of information, especially if they are highly correlated, because you know the difference between the bounds is going to give you, okay, this is your error. That your tail must be between those 2 values. And if you combine all these methods I have explained together, you can get very accurate representation of the tails, as the mains collaboration is showing here. There are other methods. For instance, the Fermilab and the European Twisted Mass collaboration were just replacing the tail by a fit to the same correlator. And this is also very useful and gives very good results. Okay, instead of integrating the numerical values of the tail, the lattice data we have, you can just integrate the result of your fit function, which should be accurate enough. Okay, so for certain time, we call T star on. You just replace your lattice data by a fit. So this is one of the challenges we need to face, but another very big challenge are the finite volume corrections. And this is because, you know, the data large time is important and a small Q square. So, and I also explained that, you know, the larger your volume is, the better control you have over the low Q square region, because in the lattice, everything is discretized. So you can imagine your minimum momentum is given by 2 pi divided by L, where L is the size of your lattice. Okay, so just the size of your volume has a big impact in this small Q square region, right? And since we have a limit on the things we can put in a computer, okay, we need to deal with this finite volume correction somehow. Actually, the very light states like 2 pions are going to notice that they are living in a box. So we have several strategies to deal with this. One is to use chiral perturbation theory and model these finite volume corrections with it. This works very well if you go to very high order. I mean, next to in order calculations are clearly not enough, as I will show in the next slide. One can use an improved model. For instance, there is one called the Lelouch-Gurnari-Sakurai that can describe accurately 2 pions in a box. And this gives better results than naive chiral perturbation theory. Or one could just do a non-perturbative calculation using lattices at very large, with very large boxes. So the state-of-the-art calculation for G-2 uses lattices of around 5.5 or 6 Fermi. And state-of-the-art finite volume correction calculation, we use lattices at around 10 Fermi. Of course, you cannot generate all your ensembles at 10 Fermi. That's super expensive, but something you can do, and I'm going to show you what BNW in this very impressive calculation we're doing. Something you can do is you can use a reference ensemble, okay, and then you take you do another calculation with exactly the same parameters except for the volume, which is larger, and you compare there, and from there you can extract the value of the finite volume corrections. So this is done by 2 collaborations, but the BNW collaboration went one step further to perform even more accurate calculations. They divide the finite volume correction, which will be given here on the left, by the value of the anomalous magnetic moment calculated on a hypothetical infinite volume. With respect to the calculation they are doing at their reference lattice. This is the correction, okay? They divide this correction into terms. One that is going to be computed on the lattice non-perturbatively, and another one which is going to be computed by the models. And in order to do this division, they introduce a lattice calculation at a very large volume, okay? So the difference between the large volume calculation and the reference calculation is done non-perturbatively. And then the difference between the infinite volume calculation and the large volume calculation is going to be very small, okay? Because at this lattice sizes, the finite volume corrections are going to be tiny. And you can use models, and then it really doesn't matter which model you use, because the correction is so small that most likely any model will take it right, okay? So this is these are the numbers they have. For instance, this is the lattice calculation, and this is the result, which is very accurate. If they compare with models, for instance, the chiral perturbation theory and next to nil order is clearly not enough. It's not representing well the lattice data. You need to go a higher order, and then it looks much better. And if you use a more complex model like Lelouch-Gurnari-Sakurai, then you get also a very accurate value. Now, for the correction between the large volume and infinite, you can use anything. They stay with chiral perturbation theory and next to in order, and you can see that this is a small addition to the final value. And this is their final value they quote, which has very impressive errors. There are many other challenges. I'm not going to go deep into that, but you can get an idea. For instance, when we perform our chiral continuum extrapolation, I mean, we take our data generated at finite lattice spacing and physical pion masses to the right pion masses and 0 lattice spacing. One will need to generate many light ensembles, and this is very expensive. I mean, you want your pion mass to be physical. Some collaborations even go lighter. You will need at least 3 lattice spacings to have good control of the discretization errors. 2 lattice spacings is not enough, because you will have just a linear fit, and this is not going to work. I will show a few slides later, and this makes the analysis very costly. it's important to take into account the disconnected contributions, and there are not many collaborations working on that right now. These are computationally very expensive, and it's important to calculate this at least up to strange contribution, essentially because there is a huge cancellation between light and strange contribution, and if you do both calculations at the same time, the errors are greatly reduced. Then I want to mention isospin breaking corrections, which go in two ways. There is mass isospin breaking you need to take into account because the up and the down quark have different masses. This can be done perturbatively or non-perturbatively, okay, and they are normally well under control. And then there are the addition of the different charges of the up and the down quark. I mean, we could include QED effects in this calculation. These are really hard to include, especially if you try to calculate them non-perturbatively on the lattice, because you know, when you introduce QED, you introduce photons, and your finite volume effects become even larger. I mean, the photons certainly are going to feel that they are living in a box. Okay, they want infinite volume to be free, and also you need to deal with gauge fixing because your charged particles on the lattice are not going to be gauge invariant, and so on. I mean, there are a plethora of complications. Of course, at the level of precision we're reaching, you want to have a very accurate scale setting, which means when you are determining the lattice spacing, you are performing your simulation at, which is given by your coupling, okay? And usually we were resorting at decay constants to fix our lattice value. So normally what you do is you compute something on your lattice, for instance, the pion decay constant, and you obtain a value in a lattice, but this value is given in lattice units. In order to relate this to a physical value, you just go to the PDG, take the value of f pi and say, okay, this number on the lattice translates into this number in nature. So now I know my scale. And this scale can be used to transform any other number on the lattice to any other number in nature, okay? So most recently, other collaborations were using the mass of the omega because it's more accurate to determine to define their scale. And the latest lattice approaches were doing something very weird. They were computing something that only exists on the lattice, but they were relating it to other physical quantities, okay, in order to obtain a physical value. And this quantity we're working on now is called W0. And this allows for a much more accurate scale setting. Finally, of course, you need to take into account contributions from other quarks that are not very light. For instance, the strange, the charm, and the bottom. The bottom is usually a small correction that is calculated after the fact. And there is a general agreement for the strange and the charm contributions. So these are more or less under control. Now, to perform cross-checks on the lattice, normally you will wait until a collaboration has finished a calculation and then compare values. But these calculations are very long and expensive, so we have developed a method to perform intermediate cross-checks that can be very helpful to nail down the systematics of our lattice calculations. So this is the whole integral for the hadronic vacuum polarization, but we could split this integral in 3 regions that will address different systematics. There is a short distance region, okay, that deals with you know, these discretization effects. There is the intermediate region where most lattice calculations should work fine, and there is a long distance region which will be more influenced with the treatment of the tails. And of course, the sum of all these regions will give you the final value of the hadronic vacuum polarization. So what we are doing is we are using these sigmoid functions to weight our integral, okay? And I can show here how this is done. For instance, I'm weighting if I weight the integral with the sigmoid region at large times, I get the long distance region. If I do this with the intermediate sigmoid function, I will get the intermediate region, and with the short distance the same. Okay, this is the latest comparison we did of our intermediate results. This was done in November 2020 in a hadronic vacuum polarization workshop for lattice calculations. I was one of the organizers, and as we can see here, we still need to work out some issues. I mean, there are several calculations now in the intermediate region where we will expect a relatively easy agreement, but there are some disagreements here between the most precise calculations. The short distance window looks fine, except for this result. I need to check if these guys include ratio data, because that could explain why it comes so different. But because I know RBC was doing a calculation mixing lattice and ratio data in order to improve their statistical errors and the final errors. And then in the long distance region, there is a general agreement. Of course, we need to agree on what we are comparing. We're not comparing the whole value of the g-2. We are using the isospin symmetric light contribution only, and we are checking the connected part. We are disregarding disconnected contributions and the contributions coming from strain, charm, or isospin corrections or anything. And of course, we do the comparison in the chiral continuum limit. I mean, we don't do the comparison in partial lattice results because that doesn't make any sense. Okay, but we can
Alex, I think we have lost you. So
this is a summary of the results. Yes. Oh, sorry. Yeah, this happens from time to time. Your voice
stopped longer than usual. Yeah. So
okay. So where did you lose me actually?
Yes, 20 seconds or so.
Okay, so I was just saying that we have.
Slide.
Yeah, we have agreed on the quantity to compare with these windows. I mean, we are not comparing the final calculation, but we have agreed to compare the isospins and only the connected part. And of course, so in order to make sense of this comparison, we need to compare it in the chiral continuum limit. I mean, we cannot compare partial lattice results. We need to take the continuum extrapolation in order to make a meaningful comparison. So yeah, I wanted to comment on the current state of the g-2 calculation. So this black point is the white paper result, and we have this very recent calculations using dispersive methods. And then there are many calculations that are not used in the white paper. And I'm showing here, for instance, the RBC calculation I was mentioning earlier that may have used ratio data. There is an RBC UKQCD calculation that mixes data coming from dispersive calculations and the lattice. So there is no surprise that they have a good agreement with the ratio data. But of course, the beautiful thing will be to have a pure lattice calculation. And these are still have large errors, as you can see here, with the different points representing the result of different collaborations. Of course, there is the BMW result that must be looked at carefully. They claim much smaller errors than any other collaboration. There are certain parts of their calculation that are very solid, like for instance, the finite volume corrections, but there are other parts that are a bit suspicious, and you should look at them very carefully, and you should wait until there are other lattice results that corroborate this result. For instance, they show very small statistical errors. Again, you can see that in these points. I mean, these bars are the statistical errors, okay? And these are the green points these are the raw data, okay? But this is their continuum extrapolation, and you can see here that the discretization errors are really large, in the sense that this is the final result of for instance, the light core contribution to the g-2 to the numerous magnetic moment of the muon, and the dependence with the lattice spacing is huge, okay? They calculate corrections to have a much flatter dependence. But when the corrections are so large, you need to be very careful when you do this, right? So this is something to take into account, and that should be looked very carefully. There are also some tensions between different lattice calculations in the intermediate window comparison, the golden window for the lattice. So these BMW results deserve further study before, you know, saying, oh yeah, we have these great values from the lattice with these tiny errors. And another source of tensions, I mean, I will call this unexpected consequences, is the hadronic running of alpha electromagnetic. Well, as you know, when you compute the running of alpha, you need to take into account several contributions. One of them is the hadronic one, which can be calculated using the you know, this dispersive data. There's dispersive ways to calculate this. And if we compare the result coming from the ratios of this hadronic running of alpha with the electroweak fits, we find a more or less agreement within 2 sigmas, okay? And now we compare it with the guess based on BMW data. We also find agreement. It's not bad, but the weird thing is that the pool goes in a different direction. So the electron width fits want to lower the ratio data, and the BMW value wants to move the ratio data higher. Okay, this doesn't look like a big deal, but we need to see if in future calculations this is going to grow or it's going to disappear. Okay. And as a summary, there has been a tremendous progress addressing the systematic on the lattice, and we are targeting the per mil precision in this hadronic vacuum polarization calculations. Of course, there are a few requisites we need to fulfill in order to do these calculations that make them very expensive. I have commented them in detail before, but we are getting there. And the cool thing about these calculations is that since everybody uses their own methods and their own regularizations, cross-check among different collaborations provide a way to keep in check the systematic errors. So you can expect very interesting results from lattice QCD during the next 4 or 5 years, maybe. And I wanted to use my last slide to promote a bit the muon g-2 third initiative that Pere was commenting on. And this is interesting. I mean, it's telling you that this g-2 thing is becoming very serious. I mean, we are taking it very seriously. So we are conglomerating people that work on experiment, on phenomenology, and on lattice, and in order to find a solution to this, to find out what's going on with g-2. So there have been 6 workshops since 2017. There was the white paper that Pere was talking about, and there is going to be a workshop in the summer 2021. And if you are really interested in this topic, I will, since this is virtual, I mean, you don't need to ask for money to travel there, and I think it's free. You will do very well registering it. Most likely there will be at least a couple of talks you are interested in. So this is my part, and I'm going to give the control back to Pere.
Yeah, thank you, Alex. That was very nice because it nicely connects what I wanted to say. I just want to spend 2 or 3 more minutes and we are done. But I just wanted to say that what Alex was commenting explains very well what is the standard model situation, I believe. No? This is the BMW result he was commenting just right now. Those are the dispersive approaches based on experimental data. And as you see here, there's a brown point, which is using tau data. And the tension between standard model and experiment in the g-2 could also be translated into the tension between the lattice tau data and E plus E minus data. That's been a long discussion since many years. And I would say what lattice colleagues are telling us, as you can see, not only BMW in cyan, but also all the average in blue, the other colorations Alex was commenting, is that we do have a problem in understanding the E plus E minus data. If you would say neglect Clio data, then you would go to the right very fast, almost in 10 units in this 10 to the minus 10, and approaching very much the lattice results. No? So I do believe that the lattice and the phenomenology is working to understand better and better what is the meaning of the standard model. On all this discussion, I already commented that, so I can skip the light by light. Light by light is right now very well understood. I just skip it. Well understood in the sense that we know what to calculate, how to do it, what experimental data to use. We also have the counterpart from the lattice, as from Mindset, for example, he was commenting, and this is the result on the white paper that is not using yet the lattice results. But again, you can, since you are summing up many things, you can also do it in a say combine linearly in a more critical way to enlarge the error instead of understanding the systematic errors in quadrature, which I believe is not the most conservative approach. But anyway, as a summary of the discussion, no, if I may play with you guys, no, this game, that was the original image we had. And I would like now to show you, just for you, for the discussion, triggering discussion, if you have further comments, what would happen if, for the standard model, you would have taken all these super conservative approaches I was commenting, say, taking the errors in linearly and so on and so forth. So if you do that in the super conservative way, that's my numbers, you would go to a very, very larger error in the standard model, which would reduce the uncertainty, the discrepancy down to 2 sigmas. No? I believe this, again, is very conservative, but this is a way to understand these discrepancies between lattice and experimental data in E plus E minus. No? So you condense it as an error, enlarging your standard model error, so claiming for not that much discrepancy. That doesn't mean this number to vanish the central difference value, right? It's just the way you understand the standard model is not that accurate, I believe. On top, I would like to say, and taking the opportunity that Sven is here, that this is also very appealing for new physics scenarios. So just let me give you a word on that, very naive. Is that
unfortunately Sven just left.
Oh,
he had another meeting, but nevertheless, please continue.
Sorry, I just missed him. No, I just wanted to say that if you would say, okay, let me explain this discrepancy within a new physics scenario, very naive, okay? I'm using Queiroz and Shepard code for computing these things. You would see that there are two lines here, solid and dashed, green bands, one, the solid is the white paper discrepancy with respect of the Fermilab result. The other one is my own one, okay? Just to show you that if you would explain it with a Z prime boson, you would really need to have an object which has a very low mass. And we didn't see it yet at the LHV, not even at LEP. So that's ruled out. So you would like to have different couplings. But if the discrepancy, the nominal discrepancy would be smaller, so pointing towards having larger standard model contributions, then you would be, say, more, it would be more easy to accommodate the discrepancy with standard new physics scenarios. Not maybe with a Z prime, sorry, but maybe with a leptoquark. Leptoquarks of order, say, 1.5 TeV or even 2 TeV with the particular couplings would match very well with the flavor anomalies we are observing in the, for example, RK measured by the LHCb. So that's the final thing. Alex commented about the G-2 of the electron already. That was the plot, and he mentioned at some point that there's a discrepancy of 5 sigma between two different measurements. There are these two papers, one published 2018 in Science, the other one in Nature 2020, and the older result is this here, is the measurement of a recoil of a cesium with respect of a measurement of a recoil of a rubidium. From that, you get, with this formula, the alpha electromagnetic, and then you see that the difference is here. Right? And this is a slightly more than 5 sigma discrepancy. No comment at all on that respect. There's only a subtle comment about some systematics. But if you take those numbers to predict the G-2 of the electron, now that you know the alpha electromagnetic with that precision, then you see that depending on what source you use, you would see a large discrepancy, negative, which is going on the opposite sign with respect of the muon one, or basically an agreement. And that's up to model builders how to accommodate this situation. So that's all from my side, from Alex's side as well, I believe. So that's now turn off open discussion if you still have the humor, energy for that.
Thank you very much, Pere. Thank you, Alex, a lot. I think it was a very nice and comprehensive review of the situation. And yeah, please, I'm inviting the audience for questions and discussions. While you all load your guns, let me just read that. Actually, Sven had to leave, but he gave us a comment. He said, yeah, so thank you very much. It was very interesting and so on. But tau data is really outdated, he says. See also the raw gamma mixing introduced by which shifted it towards electron-positron data. So perhaps you want to comment about this.
Yeah, definitely. Yeah, that's a very good point. Tau data is old, 2009. That's not super updated, but old, but it's already old. And then you do there, you have a problem. You want to have E plus E minus. So you want to have neutral intermediate state, pi plus, pi minus. From taus, you are going to measure pi plus, pi naught. So you do have to change the pi naught to a pi minus. No? So you are going to do it mechanically with a formula to do that. And this is goes under the name of isospin breaking effect. That's under control. You have to calculate, but if that's under control, you do that. Then you will see that the data is, even though it's all data, is very precise. That's why the tau data results I showed you in one of these slides are very much have smaller errors. No? What happens is always this discussion. What enters in the loop seems to be pi plus, pi minus, for which you can access from your data, not pi naught, pi minus. No? So you are introducing potential systematic errors. And there was this, I would say, naive rho omega mixing model that Jägerene used that, in my opinion, was giving bad credit to the tau data. Not, instead of, say, helping, it was on the opposite. Let me also add that if from the many collaborations you have for the plus and minus, you would take the one that contributes the lowest, then you would have an agreement with tau. No? So you can either blame to tau data, you can also blame to E plus E minus data, and that depends a bit on your taste. It's very tricky at the end of the day.
So just to close on this, are there any prospects, although we have a raised hand, so Jose Luis, of course I noticed, but let me just ask, is there any chance that we have some progress along the directions of getting new light on this tau data, right? So trying to get a handle on this isospin corrections or new data?
Yes, there are three lines. One is Bell2. Bell2 machine is going to measure this tau with even much more precision. One. Second one, Babar is going to analyze the full recorded data for the plus D minus. That would be very interesting. And then we have the in Russia the Web 2000 machine, which with two different collaborations, SND and CMD, that they are going to release data for that channel as well. So there will be these three fronts soon competing with the old ones. And we hope also the Chinese Best 3 is also going to do new runs on that. So soon we'll have a lot of new data.
But this is experimental data. So there's always this, so one would always be tempted to say, but you always have this isospin correction, right? So is there any, so can we go any farther about this? Is there any way of trying to estimate the corrections or systematic differences between pi plus and pi plus, pi minus?
Yes, I believe, yeah, you are right. You calculate that, it's a loop process, you calculate it once and for all. That's a sort of kernel. And what happens here, that the optimal way would be to have different channels from taus and E plus E minus data that would use exactly the same kernel for changing the isospin, and then compare all of them. Do you see a systematic difference or not? We are only having one channel now comparing at that level, no? So would you blame to the formula you use for the, you say, no? You would really like to have different channels, and I believe this is a prospect. Really comparing the machinery, no? I believe the calculation is correct, but there's many correlations, no?
Thank you very much. So, Jose Luis, would you like to add something?
Yeah, I have a question for Alejandro. Taking into account the long list of challenges you have mentioned in the lattice attempt to calculate the hydronic vacuum polarization and hydronic light by light contributions, what would be, in your opinion, a conservative estimate for the uncertainty on the lattice determination of these contributions? Do you think that one can still claim that there is an anomaly?
Well, let me, if Pere allows me, let me go back to the.
Okay, I think that Pere gave me already his answer to my question, but I wanted to know what is your answer.
Yeah, well, look, the precision right now is not great. The only exception is this BNW calculation. Okay, and we are a bit suspicious about this calculation. So I would say, unless you have several lattice calculations done by different groups, and this different group thing is really important because since different groups use different methods, then you have a cross check of the systematics. Unless you have different calculations done by different groups, so you can contrast, you can compare, then I will keep this result a bit in the air, okay? And if you leave this result out, everything still is a bit early. The good thing is that, as I mentioned, in the following years, we are going to see a large increase in the precision because now we know much better how to do things. We just need to have more computer time, and we will crank this out. Okay, but at this moment, I wouldn't say there is a definite answer coming from Larynx. Like, oh yeah, look, Larynx confirms the Fermilab experiment, or lattice is closer to the ratios. I wouldn't say there is such a statement.
Okay. So what is the time scale for you guys? So
Well,
what is the time for a
Larynx,
cross check that can say, okay, we are doing something better than BMW?
yeah, well, I mean, these calculations take take some time, not as much as experiments, but I don't know, maybe something between 3 and 5 years. Most likely, we'll have interesting results for several coming from several collaborations.
And
I mean, this is normally the time scale of a Larynx calculation, a big Larynx calculation.
But these things are, I mean, but people has been working on this already. So these 3, 4, 5 years are already so starting from the past, in a sense.
Well, yes and no. I mean, there are some collaborations that have been working on this for a while. For instance, you can see BMW published in 2017 and in 2020. If you want an update from them, if they keep working on that, because sometimes BMW, when they publish a result like this, they say, okay, now we switch to a different thing. Yeah. Then it will take at least this amount of years. Also, you need to take into account that many of these collaborations are working on several projects at the same time. So, for instance, I'm working on Fermilab. We have this result from 2019. We are working to improve this very hard, but we have many flavor physics projects that are also very interesting for new physics, and this lack of manpower slows down us a lot. So I don't know. I will expect by, I don't know, maybe 2022, 23, maybe some collaboration has some results, and by 2025, most likely we'll have a comprehensive comparison. Maybe I'm a bit pessimistic. I don't know, but. Not long. I don't think it's a long time.
So along the lines of Jose Luis, so let me just ask another provocative question. What do you consider? So let us have a little fight here. What do you consider is the most accurate standard model prediction at the moment? And you can just so let's go down to the lattice and do everything from first principles, but then you have to cut integrals, you have to do next to leading orders, you have to do at the end you have to cut your you also have to do something which is not strictly QCD, or at least cut your let's say cut your calculations into so many pieces that can go wrong, or just use experimental data which exists, right, and use theory to recompose a calculation. Of course, we see here in this graph, we see the errors are different, right? But do you agree with this? Do you agree that lattice at the moment is really is much worse than these other indirect methods?
Well, yes and no. Okay, so first, if you use experimental data, then you are not fully standard model prediction, right? I mean, your prediction is not essentially standard model; it's something else. But they might reveal some tensions. Okay, like here, for instance, there are two experiments here running, because these dispersive calculations, of course, they are based on standard model relations, and you are verifying something there. But you use a lot of experimental data here, and you use a lot of experimental data here. Okay, and if there are some tensions, it's telling you that something in the middle is not working well. But the advantage of the lattice is that it's pure standard model. I mean, you take QCD and you simulate that. And yeah, you mentioned that the calculations are so complicated. You have to do some approximations here and there and then correct. But the good thing of the lattice is that everything you do is under control and is systematically improvable. I mean, you don't have a theory, a complicated theory that you don't know very well how to estimate your systematic errors. And then you quote an error that you believe is accurate, but it is not really very accurate. On the lattice, if you do things right, your errors are accurate. That's why lattice results are valuable, okay? Because when you see these error bars are accurate, okay? And that's why we want to review very carefully the PNW results, because if they have done things right, very carefully, there are no criticisms to their calculations, then this is a lattice result, and this is something you should take very seriously. But for the time being, we are just checking, looking for loopholes in their calculation. One is something I mentioned before. They have large discretization errors that are being corrected there, and you need to see they have done this properly.
Discretizations or large volume?
No. Well, actually, their finite volume corrections are very impressive, and I think they are very well done. But the problem I mentioned, let me find, where is this? Okay, here. When they take the continuum limit, okay, yeah. This is I mean, this is a function of the lattice spacing, and you see that this data here, it depends very strongly on the lattice spacing. This tells you there are large discretization errors, okay, going on here, and they use some.
Actually, I wanted to ask you here because of course the green points they have a very strong dependence, but it is not the same as the other lines, right? So I wanted to ask you for more details of this graph. So are all this data fitted with some model that explains all the lines at the same time, or each line is independent?
Yeah, well, you know the discretization errors.
By the way, Jose Luis, please, if you have some comment, just jump in at any time.
I don't want to interrupt you. I mean, okay. Go ahead.
Okay, so let me go on with this, and maybe then Jose Luis can comment. So you know the discretization errors of your regularization. For instance, in this case, they know the discretization errors go with A square. Now, this is very general, right? There can be a huge coefficient in front of this A square, or there can be a small coefficient. You know that your ansatz for an extrapolation will be at first order A square. Then there can be higher order terms, okay? And actually, one of the things is that how important is the A to the 4 term in this data, okay? One of the things we are discussing. So in this case, they know this is going to be with A square, but they perform some corrections to reduce, let's say, the coefficient in front of this A square extrapolation. And this is how they get the blue and the red data, and then they perform some sort of stochastic approach. They do many fits, and this is the result of their fits, and they perform they do these histograms, and with these histograms they extract the central value of the error. Okay, we are just checking this because essentially they are doing a huge correction here, and this is a bit suspicious. That's
yeah. Alejandro, I don't understand well your. I mean, why do you claim some supremacy of lattice, pure lattice calculation compared with a calculation that use partially some data? I mean, I understand that when you use data, Okay, it is implicit the assumption that the standard model explains the data you use. So what you are using is, in fact, some relation between something that you could calculate directly or relate with something that you observe, that you have data. I don't know why do you prefer a purely lattice calculation without any use of data?
Because a pure lattice calculation is a pure QCD prediction. That's all. I mean, it's not any claim of a supremacy. It's just to have under control what you are doing. So as you said, for instance, if we use here a ratio, we use a dispersive approach. We use this scattering cross-section data, and we use the optical theorem. We are testing some parts of the standard model, of course. But if you perform an experiment where some standard model is involved, of course, because for instance in this Fermilab experiment, you know you have all these equations about how the muons behave and what you expect to see, that there is a standard model involved there, and you compare this with a pure estimate coming from a standard model. If there is anything that can go wrong there that can show you a difference, you will see it. In the other case, when you are comparing different approaches with different experiments, you might see the difference, you might not, because maybe for some reason the new physics are not in those particular cross-checks you are doing. So it's not that I don't think it's superior, but I think this kind of pure theoretical calculations are really necessary, especially when doing this kind of searches for new physics.
But the mixed approach, if you find some discrepancy, then you know that there is something beyond the standard model. Probably, okay, you don't know if it is in the
exact. That's the thing. You don't know in which
if it
process.
Is in the calculation of the cross section, or that you are using in this dispersive approach. But something is. You have to go beyond the standard model anyway.
Yeah. So
exactly, I agree with that. I mean, I'm not contesting that.
But it gives, so the lattice gives you an extra piece of information that there's new physics contributed to the measurement, to the g-2 measurement, right? While in the other case, it might be that new physics is happening, and so you have some new particle in E plus E minus that you have not discovered. It's something that we worked some time ago, so they can be very weakly charged particles that are Pere produced, but they escape the detector. They contribute somehow, or some other neutrals, or something like this, right? So very weakly interacting particles that were produced there, and gave you some contribution to the inclusive. And then you think that your g-2 is the problem, and it was actually the old data. But nevertheless, I think both. I'm very happy that we have both, right? Because once two or three of them they agree reasonably well, then we can pinpoint new physics in the other.
If I might add, no, my take on that is the E plus E minus data may have, when looking at the lattice results, the E plus E minus data may have an underestimate error, a purely systematic error. So those red squares here would have a larger error band. That's all, no, and that's why the lattice must talk to the dispersive results, no, and get this discussion, no, triggering fostering this agreement, no? So I think this is a win-win situation. As I said, no, I still believe that the difference, the numerical difference that we are observing is 25 units 10 to the minus 10, when the full electroweak sector is only 15 10 to the minus 10. So you are seeing a discrepancy that is much larger than the full electroweak sector. That sounds weird, no? That you wouldn't like to have, either you have a very light particles, or you have a very heavy, super strongly coupling particles, no? So it's not really, I would rather prefer to have a smaller discrepancy, numerical, the distance will be smaller, so you can easily accommodate either light particles weakly coupled or heavy particles not that strongly coupled. Right? So what I'm saying now is that I do like the result of the lattice because it points toward this idea that the distance is smaller. Meaning that in E plus E minus we have a problem, that it may not be new physics there, it's just simply that we have a systematic to have, we still have to understand how the standard model works and how to understand the data. No? On top, you like to accommodate other anomalies that you are seeing, no? As Alex was commenting before. No?
So perhaps another question would be whether the particles that could accommodate the tension in G-2 could also explain some other tensions, and perhaps some of us, you have an opinion on this, or do you know how many birds we can kill with the same stone, and with which stone?
Yeah, it's very nice. So if you want to explain G-2, forget about the electron G-2. If you want to explain the muon G-2, depending on the model, you will not be able to explain RK from the LHCb. Then you will have the Cavivo angle anomaly that will not be able to explain either. So you have this triangle of things, 3 anomalies, that if you want to explain them all together, you have a problem.
So I think last time you came here, we were talking about light leptoquarks or intermediate mass leptoquarks.
That would be fun.
Could they play roles in all this, in all 3?
The leptoquark, but it must be a massive one. It's a natural candidate because if it's been very much elusive in the LHC direct searches. But the idea of looking for the light particles, I'm not sure that anyone has explored that systematically. So I do believe it's a good opportunity. We are really pinning down now the G-2. You have now a particular number for that, which is robust. And then you have these other anomalies. So might be the time. I don't know. I don't know who did that. But it would be very nice. You see, you take the other anomalies, you predict what would be the contribution to the G-2. And if you find that the contribution is smaller than the discrepancy, you have a bingo here. I in favor of what I was commenting before, that you would expect I would expect in the future that discrepancy gets numerically reduced. So it will be very
I would like to raise another point. I mean, it's not for the 2 speakers, but perhaps for some experimentalists in the audience. Do you know of any? I mean, we talk always about how to move the theoretical result for G-2 and see if it can get close to the experimental value. But are there any ideas or attempts to find some loophole in the experimental determination of G-2? I mean, on all the ingredients used, such that perhaps the real value of G-2 could be smaller than what they claim? Do you know of any attempt in this direction? Or because it's not an easy work. I mean, how they get this experimental result with such precision. I mean, there are many.
Perhaps it's the right moment to talk about this penning trap Japanese experiment.
Yeah. I do have this slide if you like. Safe.
Yeah, give me a second. Yeah, actually, this is what I was mentioning, that it would be nice to have a totally different experiment with totally different methods, totally different systematics that could cross-check Fermilab and BNR result. Sven was claiming that these 2 results are completely independent. I wouldn't say they are 100% correlated, but I wouldn't consider them totally independent because they are just using the same methods. So if there is a different method, then that would be great.
So you see, I give you here the archive number for this project. That's the full project. And this is the sketch of the system. That's a penning trap. That's a standard penning trap. And then you have a LINAC with muons. And I think this is a table of systematic errors and so on. This is the sketch. So you will have the very slow moving muons, you see. They will go few MeV instead of 3 GeV, few MeV. They will live very shortly, but it will be enough to just reach the penning trap. And then you will have that's the method. How to focus these things, and then you will have this thing. No? So you the mu enters, and then decays into a positron and neutrino and so on. So forth, no? And that's a very small detector, as you see. What is very difficult, as far as I understood, is the having so strong magnetic field. Should be 3 Tesla, which is it's a lot. And those are some simulations, what they expect to find. He's using cold muons in that respect. Completely different setup. You see, slow moving muons, a lot of muons.
Different, but yeah, surely the method is just the precession of a spin.
That's always.
Of a magnetic field is the same thing, and the spin of the muon you determine from the E plus distribution in the decay of the muon.
Correct. Yeah. At the end of you're right. At the end of the day, it would be the same physics.
Yeah.
But you are trying to be at least at a different energy scale. So
yeah, there's a big difference.
Yeah, that's true. I mean, that may be related to your question. When Brookhaven and Fermilab, they do measure, they use this magic energy. Right? That's a formula that is purely classical electrodynamics. You have a mu there that is calculated to so many loops. But the only thing that it knows about quantum field theory is a mu. The rest is purely classical. So how do you know?
Yeah, this is something that actually calls shows alarms, right? Or make. So how do we? So if you just allow, if instead of writing your classical field theory with the classical Lagrangian of electrodynamics and your charged particle, you start writing more or high order interactions in which are suppressed by powers of all the particle masses and all the relative corrections that you are introducing. Don't these extra dynamics change the classical trajectory slightly?
I don't know. That's what I would imagine. You have a beam of muons. I mean, we are talking about alpha to the cube effects here. Alpha to the cube is important. Alpha electromagnetic to the cube. So you have many muons traveling all together, but they should be separated enough in order not to spoil the collective behavior, no?
Well, that's another thing, right? You are not taking, so you are not doing the measurement one muon at a time.
No.
But these things can be, at least collective effects can be estimated. And I guess somebody has done this already, and they can have more or less this under control, I hope.
Hopefully, yeah. No, sure. But still, no?
But I would like to make a comment. So this is accelerator physics, and accelerator physics is classical electrodynamics for this purpose. So it's correct what they do.
So I do believe that is correct, but that's the wondering, no? If they match the, so they calculate, so we calculate what they measure. That would be my question, no? So I do believe that they are doing the things right, but then you say I'm calculating what you measure, I compare. No?
By the way, what is the energy of the muons when they enter in the penning trap? It's very low. It should be very low, no?
That's very low. It's
otherwise will not be trapped. That's
true. It's MEV scale. You're referring to the JPark setup, right?
Yes, JPark.
Yes, that should be, it's MEV, so really, really slowly moving muons. And they will live very, very short.
Talking about lifetime of muons, let us talk about lifetime of the experiment. So when we will have, when can we dream of having experimental results?
For the JPark, they promised 2024 to start the calibration. But it turns out that these people in the JPark facility know a lot the technology. That's why they are doing it there. Because they are using gels, muonic gels, whatever, that they don't know. And it may be fast to the calibration. So soon, I believe, say 24, 26, 27, if they go as Fermilab, 3 years to get numbers. At that time, we may have run 3 from Fermilab already analyzed. So, a lot of pressure.
So I guess these are the time scales for the hype, something like 26 or 27.
Yeah,
we will have we'll have a lot of pieces, and by then also lattice will be
beating.
And so by then we should have our funny theories, our funny theory that tries to explain all these things.
Yeah. So let me advance the final the end of the film.
Show us your crystal ball.
We are in 27. We have new experimental results from round 3 from Japan, and we have better estimates of the theoretical result for G-2, and it is confirmed 5 sigma deviation, more than 5 sigma deviation without any doubt. So we can conclude that there is physics beyond the standard model. And how do we go on? I mean, what do we learn from this? I mean, it seems to me that you don't have a clear guide how to explain this discrepancy. I mean, the example is the number of papers that we have read in
2 weeks,
in a few days after this first data. I mean, there are plenty of different directions, completely, unrelated, that can explain this discrepancy, and you don't know.
You don't know. That's very true.
But Jose Luis, if you are right, most likely we will see this somewhere else as well. Like there are a lot of flavor physics experiments and lattice calculations that we're trying to cross-check things. And these are, I think these are better focus in the sense that when you find a discrepancy there, you have an idea of where it might come from. So maybe by 2027, you find several, not just one, several results that tell you there is some new physics here. Maybe you don't. You know, the standard model, you want to look at it in that aspect that everything looks fine in the end. But if you find new physics, I think I'm cutting again. If you find new physics, most likely you will find it in several places, I think. At least in a short span of years, maybe not everything at the same time, but not in long time scale.
I don't know. But from here to 27, I would say maybe B physics would be the only possibility, and I'm not so sure that even if you take these two things together, I think that you still don't have enough guide. I mean, there are still plenty of different ways you can try to follow. I mean,
Jose Luis, your point is very clever. If you are looking for a quintessence to explain the expansion of the universe, that's not going to be the answer, because you cannot distinguish whether you have a new force, a new particle. It's a new particle interacting with the same rules and the standard model. It's a different interaction, and in that respect, I'm not fully agree with Alex saying that the flavor physics may help either, no? See, there you also have ratios of things, so you can all explain everything with whatever model you came up with, no?
Well, it was an example because I know, I believe people are more focused there than in the sense that there are more clear directions than in G-2, but everything could come maybe from, I don't know, actions, you know, I mean, there are many, there are many research lines, and I think that if there is something to find out there, we might find it soon, and we might find it from several, several different experiment, theoretical estimates, whatever. Okay, so and in the lattice, we are working very hard because I think if you find some discrepancy between lattice and experiment, this is really a clear signal because of what I was commenting before. Beautiful thing of the lattice is that it's pure standard model.
Yeah, definitely, Alex, but still, no, it is not a direct search. No, it's indirect. So, what is this? And then, what are you learning?
Yeah,
that was, I believe, Jose Luis' point. No.
Yeah, that is true. I mean, yeah, that is true. The point is that direct searches are are complicated. I mean, you see there was a lot of hype with the LHC, and in the end, nothing is coming out of there. And this is because, you know, when you look at the scales, if you want to find new physics for sure, you need to go to a very, very large energy scale, and this is unfeasible. So you can explore a tiny region with these huge accelerators, and it's great that you are doing that, but you have much higher chances of finding something with an indirect search. But of course, then it has its downsides that you don't know what you are finding.
Yeah. This is my point. I mean, the point is that if all that you see are virtual effects, indirect effects, it's very difficult to identify what is behind this indirect effect. I mean,
but that gives a lot of jobs, right?
This gives a lot of jobs, and this gives great motivation to continue to continue doing another indirect experiments until we can do a direct experiment, a direct search of the relevant
phase space.
Actually, it might, a new collider might not happen. A really new collider might not happen if some of these anomalies doesn't pop up, do not pop up. And what do you think, Sian? I think. Oh, see, you have to unmute your microphone.
Yeah, we don't hear you.
Pensaba, a lo mejor podemos saltar al castellano, o hay alguien en la...
Yo creo que no, sí que estamos...
Lo que queráis, es sobre todo por el canal de YouTube, aunque normalmente
Sorry.
En muchos seminarios no se graban las preguntas, pero creo que las estáis grabando.
Shanna has problems with the microphone.
In the effective field theory approach, then you would say, okay, I just put a five-dimensional operator with a coefficient that fits the difference between G-2 experiment and theory. That's all, and that's all you get from this point of view. This is just a model-independent approach to new physics. But it tells you nothing about what is.
That's true. Then you would like to use that to predict other things. Start constraining and see the symmetries. I believe the symmetry would be the clue point. No? If you can observe symmetries in these operators, that then may bring you, they define the proper phase space for these new objects.
So what is the king of the explanations at the moment, in your opinion?
Leptoquarks, I believe.
Leptoquarks.
See, vector leptoquarks. That's what because they are the most elusive ones, I believe.
That's very interesting. If
you answer this thinking on g-2 or not?
Yes, I try to combine in my head g-2 and this RK from the late CB.
Yeah.
All these anomalies in the flavor sector.
Yeah, for RK I understand, but if you take only g-2,
no reason at all.
There's no reason.
No, the nice thing of the leptoquarks is that in a way you can easily tune the couplings to accommodate the data without further problems in other sectors. Yeah, Z prime, for example, was not observed. Then if you tune these things, you may spoil other things. For example, the mass meson mixing of other sectors, no? But with the leptoquarks, then you can exclude, so you can evade these other problems. No? That we will see.
The nice thing would be to see something that leptoquarks do something nice from a theoretical point of view. I mean, just not only from phenomenology, but
not only existing, but just connecting different phenomena.
Yes,
unifying something in a beautiful way. But let us not ask nature what it is to be of our liking. So, and the question would be, so what are the other experiments that we can do, which are completely different from g-2, that would tell us whether these leptoquarks exist or not?
Well, actually, there's a very nice initiative at CERN that is called muoni. That is a scattering muons against electrons in the space-like region, or in the space-like kinematics. There you would expect all these things, that the same things to appear in a very well-controlled environment.
So
that's what they believe.
But can they reach the required energy? Required energies?
It's not for energy, it's also indirect search, but because you are only looking at the angles. But the way you mentioned very, very precisely the angle of scattering.
Okay, I see.
And it would be like a running of alpha electromagnetic experiment, but open-minded, believing that there's lepton flavor universality violation in nature, so you would see it there. No? So you're really putting muons and electrons at the same time. Which is actually maybe, again, the problem in g-2, that we are using E plus E minus data for a muon. So it's a muon line. How do you know that a muon, a mu plus, mu minus would have exactly the same vacuum polarization, exactly with the same scales, so forth and so on, no? So that's, I believe it's what they are trying to really prove. No?
Systematics, yeah.
At CERN, they have the beam, the muon beam, and I think it's just using some infrastructure which is already there. They have to set up. But I think it's quite nice.
Very nice. So actually, we have plenty of prospects for the next year. So it looks like this thing is going to go, can potentially grow, and we are going to have many different results in 3-4 years. And I guess your agenda will be quite busy.
Hopefully. Hopefully.
It looks like, So this is the hype. So let me just ask around whether there's some other comment or question, or even perhaps you, Pere or Alex, if you want to ask or comment or say anything else, because I think we are now reaching the 2 hours plus, and some people would like to see an end to this, and in particular, probably my daughter.
Definitely.
At least yes. I would like to go and see it, and I'm perhaps I shouldn't have been the the organizer here. I should have let this over to somebody else, but at least I would like to go on another duty. But please jump.
Just further comment, Javi, I would like to thank you for this opportunity to have this so beautiful discussion. I learned a lot. Thanks also to Alex. We got some email exchanges which were very, very interesting and helped me to prepare the presentation. And I would like to finish saying that if you have further insights, further discussion, further whatever, just send an email. We have a chat. I would love to hear your opinion, further opinions, or continue discussing, collaborate, whatever you like. Okay, guys. So we are very close to each other right now with the meet, no?
Indeed, even closer than before with the AVE.
Correct.
Yeah, thank you, Javier and the CAPA for organizing this. Thank you, Pere. This was very, very nice. The way we prepared this talk. I hope you like it, and of course, yeah, you have further questions, comments. We're open to any discussion.
I'll do. I took a lot of notes from what you said, Alex. So
okay. Well, I can send you the slides. Yes.
Yeah, please
that would be useful. Yeah.
Send me the slides. I will upload them to the Indico and make them available to everyone.
Great idea. Thank you.
Yeah, but Pere, next time you put instead of unizar kappa.
Sorry, my mistake. Okay, thank you.
No, yeah, it's a joke, but we are very proud of it. So,
of course you are.
It's more specific, no? Unizar is
it's
art, history, everything. Thank you very much for your talk.
Yeah, thank you very much. It was a very nice thing proposed by Pere, but then enlarged and changed and reshaped by Alex and all of us. So yeah, let us continue. Let us be in touch about this. Okay.
Thank you.
Bye. Thanks a lot.
Bye.
Bye.